All right, well, I need to reset this other computer apparently, because I can't even run it from a command line prompt. So while we're waiting on that to happen, let's talk about cascode current mirrors. So ideal cascode current mirror looks something like this.
We can't see your screen. I don't know if you were showing on your other computer or if you were, but we can't see your screen.
Dr. Hartman, can you hear us?
So we've our cascode current mirror topology effectively just stacks another NMOS current mirror on top. And our ideal case has a independent current source providing our reference current to the left-hand side where we have transistors M1 and M3, and then our output side is on the right-hand side where we have transistors M2 and M4. Now, we don't have access to ideal independent current sources. What we're going to wind up doing is a slight modification where we're going to use a PMOS transistor biased deep in the saturation region to achieve the same result.
Dr. Hartman, can you hear us?
Unfortunate.
That voltage, V bias P, that I've labeled right here, this is just a voltage that is required to force that PMOS transistor thank you for letting me know you can't see the screen, and I guess I have the volume turned down again, because I was in a test last night. I feel, again, like a jackass. Let's see. There we go. Okay, let's see. Chat probably telling me, yep, we can't see anything and I can't hear anybody. Dang it, Ted. All right. Okay, well, now that you can see my screen, I'll give you a minute to copy that stuff down while I try to get that other computer going. Sorry about that. Yeah. Okay, let's circle back around here. So in our cascade, the output current, I out, is largely dependent on our voltages VGS1 and VGS2. Application of our top current mirror, M3 and M4, is used to try and hold VDS1 and VDS2 equal. So we have a voltage VGS here between the gate of transistors M1 and M2 and ground, where we're assuming, well, we're not assuming anything actually right now. It's fixed to be that way because those two guys are tied together. But if transistors M1, M2, M3, and M4 are all equally sized, then we would also see that this voltage between the source, or excuse me, between the gate and the source of M3 is the same as the gate source voltage for M1 and M2. So from this, we can see that the voltage at the gate of M4 is twice VGS, which could be written as twice VDS sat, our overdrive voltage, plus threshold voltage for our N-type transistors. And from this, that lets us know that the voltage at the, let's see, the voltage at the drain of M2 is then VGS. From this, the minimum voltage across the current source is our overdrive voltage for transistor M4 plus VGS is equal to twice VDS sat plus VTHN, which for our process is going to be approximately equal to twice 250 millivolts plus our threshold voltage of 0.7 volts is 1.2 volts. This is the minimum voltage needed to keep M2 and M4 in saturation. If we're not in saturation, then we don't have a current mirror. But why the heck won't electric run? Fine. That's frustrating. So now let's look at the output resistance of our cascode current mirror. So we're going to look at our small signal model. And use kind of Thevenin's theorem, actually, I believe. So if we look on the output side, something like this. We're going to tie our gates to ground. We're dealing with a small signal model. We're going to apply a test voltage, V test, across our output terminals and determine the current I test that flows in, because the ratio of V test over I test will give us our output resistance. Using our small signal model for transistor, this is M4 and this is M2. We have GM VGS4 here, parallel with our resistor R0 that's representative of the channel length modulation. This is our voltage VGS4. Of course I am. Here's GM VGS2. And the resistance from channel length modulation. Or not. Here's VGS2. And we have our test voltage. Again, this is our test current. So let's start with something pretty simple. What is the voltage VGS2?
Would it be the voltage across that? Well, or no, it's just the channeling modulation. I don't know.
What's the voltage connected to the positive polarity terminal where I've defined VGS2?
Which,
Let's say, would it not be 0?
Exactly 0, that's correct. Because it's ground.
duh.
So what does that do to our bottommost dependent current source?
It's nothing there. It's,
Right, so it's that current is 0, so we can treat it as if it were an open circuit. Right. So what's the nodal voltage right here? I would argue that it is, oh, sorry, go ahead.
It would be I test through R0. No,
so that
it would be plus the
ground. That would be the voltage drop over that top resistor R0. But with respect to ground, so if our positive polarity terminal is tied to ground for VGS4, then that means this voltage is simply negative VGS4, right? So if we know this voltage is 0, I'm going to erase this guy right here. And I have negative, positive, VGS4, like so now, right? Because VGS4 is tied to ground. Positive polarity terminal is tied to ground. The negative polarity terminal was tied to that node. So my voltage drop, the voltage with respect to ground is then at this node is then negative VGS4. So we can say that negative VGS4 is equal to R naught times I test. We can say that using Kirchhoff's current law, I test is GM VGS4. Right, so that's this current plus V test minus negative VGS4 over R naught, which is representing this current. And if we substitute in R naught times I test for VGS4, what we get, come on, computer. I test is equal to GM times negative R naught I test plus V test minus R naught I test divided by R naught which looks like GM negative R naught I test plus V test over R naught minus R naught I test over R naught, which is simply I test. So we're now going to collect I test terms on the other side. So when we add I test to both sides, we're going to have twice I test plus GM R naught I test is equal to V test over R naught. Which gives us twice plus GM R naught I test is equal to V test over R naught. And if we multiply both sides by R naught and divide both sides by I test, we get our output resistance, V test over I test is equal to twice plus GM R naught times R naught, which is going to be approximately GM R naught squared. So we're going to see that we're going to have a pretty large output resistance for our current mirror, which is actually quite good. Why won't electric run? Sorry, I'm still trying to get electric to run on the other computer so that we can do some layout today, but it is being difficult.
The program likes to be difficult.
Yeah, I have changed exactly 0 settings and things like that since I used it last Thursday with you guys. And it has just decided that it does not want to run. For whatever reason. All right, give me 3 or 4 more minutes to get this going, and if it doesn't work, then we'll jump into differential pair amplifiers, and we'll spend all day Thursday doing layouts, I guess. All right, so give me just a couple of minutes. This is driving me nuts. All right, well, I still can't get electric to run on my other computer, but I do have it installed on this laptop as well. So we'll just use this, and I just won't have the files that I had saved last time. Although I guess I could just email it to myself real quick. Let's see. So all right, I just moved it over. All righty. So let's develop our cascode current mirror and play around with a couple of things. Actually, before we do that, I brought up the basic current mirror that we were designing at the end of the last class. And when we ran our simulation on this guy, if I'm not mistaken, we weren't getting a current of 20 microamps, which is what we were expecting. Did anybody, let's see here. Let's do the drain current through our PMOS transistor. And the drain current through NMOS 1. Yeah. So we were getting approximately 15 microamps for our current mirror when we had designed it for 20. And so I suggested that we change the width of the PMOS transistor. Did anybody actually go about doing that and figure out what we needed to get it down to get 20 microamps?
I messed with it a little bit, but I think I might have done something wrong because I'm getting something like for some reason it actually shot up. So I've definitely messed up something somewhere.
Okay. Anybody else give it a whirl? All right. Well, nobody's volunteering anything, so let's take a couple of minutes and get that guy fixed before we jump into our other one. So shear electric. So I believe what I had suggested is that we try 50 microns. a width. No, not a width, a length of 50. So if I just resize this guy right now as it is, I'm willing to bet I'm going to give myself a ton of errors. Maybe not a whole bunch of errors, actually. It's just going to look janky. Oh, no, 23 errors. So that is also something. So what I'm going to do is I'm going to undo that change. And I'm going to delete some of these connections that are going to cause it to go a little bit haywire. Now, let's change it to 50. So I clicked on my PMOS transistor and press Control-I, and I'm setting the length to 50. Then I'm going to reconnect it. Reconnect this. So let's see, any errors? One error. Let's see what that is. I typed. All right, let's just see an F5. All right, minimum width height error. So it's saying that my body connection, because it is a, let's see, chunk of N-well, it doesn't have, it's not 12 wide, and that won't be an issue as soon as I wire this back up. Except that I don't want active, I want metal. And I'm going to change that metal layer to not extend like it's currently doing. I thought I said not extend. Not extend from both ends. There we go. So that should, no, still finding one error. L is less than 12 wide. Let's try this a slightly different way. No. All right, let's try this. Make this the same dimension. Scoot it over here. All right, getting no errors now. Connecting my PMOS. Select my poly. There we go. All right, so it's now got a 50 length PMOS in there. Let's see what happens when we simulate it. Let me share the right screen. So if we add our drain current for our PMOS transistor, it's getting a little closer, 17.7 microamps. So let's make it slightly smaller yet again. So I'm going to try 45 this time. So it's going to have 10 width, 45 length. Changing my body contact. And all right. What did I do? 3 years. What did I do? Let's see. No errors. Let's see. Share LT Spice. Our drain current for our PMOS. 19.5. So that's pretty dang close. So I think 45, a 10 over 45 PMOS transistor is where we need to be for our biasing, for our PMOS acting as a resistor for biasing our single stage current source there. And let's just look at, make sure that our drain current in M2 is doing what it's supposed to be doing. And yeah, so we're seeing right around a VDS of 1 volt, we're getting current matching, which is how it's been behaving the whole time. All right, so I feel like we got that pretty well knocked out. So let's talk about then making a new cell. And this will be cascode current. And specifically, let's call it NMOS, cascode current mirror. All right, so how are we going to efficiently draw this guy, right? So we know for our basic current mirror that at least the bottom stage where we had, let's see, an NMOS transistor, we rotated it, we made it 10 by 2. We need to set the spice level, or set the spice model. Let's see, control. To NMOS text size 1.5, rotation 90 to align it up top. We duplicate this guy, Control C, and Control V over here. We need to put an active region in the middle. This is the shared source. And making it 5 by 10. No errors. So we know that this basic configuration works perfectly fine. We can put in our other active regions while we're at it. And this guy over here. So I'm going to put some annotation text in just so we're all clear about what is what. So right here, this is the drain of M1. This contact is the drain of M2. This guy in the middle is the source of 1 and 2. Our gates need to be tied together and also tied to our drain. So let's put a contact here, connect them, 2 errors. What does that error say? Inactive overlaps are in transistors. So did I not connect them? Yeah, I forgot to connect them. I'll fix that. No errors. So let's scooch this guy in as close as we can. Still no errors. So that was too close. The polysilicon, which is this guy. That's too big. So I've got my gates tied together. Now I need to tie my drain of M1 to my 2 gates. So this is, if I'm not mistaken, pretty much exactly what we did for our version 2. I haven't yet done the body connection. We'll get to that momentarily. So what I'm considering now is how to efficiently connect our next transistors, right? We have M1 and M2 pretty well laid out here. I don't know how we could make it occupy less space. The lazy part of me wants to say we just copy this guy, paste it up here. And then tie things together like so. Let's see. So having my n-well overlap with n-well isn't going to hurt anything. So let's see, 2 errors. That polysilicon stub is too close to the other polysilicon, and our gates aren't tied together in this case. So the gates of 3 and 4 are tied together, but not 2, 1 and 2. Zero errors now. And our source for transistor M3 should be tied to the gate and drain for transistor M4. So if I do that, let's see here. Oh, that's not what I want to do. I don't want. So that was an error because I don't want that source. I guess I do want that source tied to the gate, so that would have worked. Yeah. Okay, well, actually, all right, so I've made a fundamental mistake here. Who can tell me what it is? Anybody got any ideas?
You're sharing the sources.
Exactly right. I'm sharing the sources on the top set of transistors, and that shouldn't be happening. So I'm going to have to scrap this whole thing up top here because I made a silly decision. So with that in mind, how can I draw this thing maybe a little better, right? So we know that, let's see, the source of M3 is tied to the drain of M1. So if I drop in another NMOS transistor, let's make it 10 by 2. It's rotated 90 degrees. I'm gonna need 2 tools to set my spice model. Excuse me. Now where I have D1 labeled is actually the drain for 1. And the source for 3. So that's a valid connection there. Let's put some inactive over here. Make sure to actually connect them this time. Let's put some annotation text here. So this is the drain. Of transistor 3. And the gate and the drain for 3 are tied together. Let's see if I get any errors here. 4 errors, let's see. But I have poly too close to a metal. So it's saying that that little notch between them is too small. So I'm going to fix that. Nope. By trying to select this guy right here, and let's change the width of it to 4. And make it not extend on either side. Let's try 5 because there's still a little notch there. And that got rid of that error. All right. It's a little awkward looking, but it still is getting the job done. Let's see. So that takes care of transistor M3's connections largely. Now I need to do transistor M4. And so I'm going to put it over on the right-hand side. So it's going to be a 10 by 2. Rotate it 90. Set it to NMOS. All right, and now this node, I want to select annotation text. This is the drain of 2 and the source for 4. The gates of these two guys are supposed to be tied together as well. So transistor M4 should be tied to transistor M3. Making that text a little bigger. And so what I'm going to do is I'm going to put a contact down here. I'm going to move it in as close as I can, like I did before, which I believe should be okay just sitting right there. We'll find out. And I'm going to put another contact right here. Tie these guys together. That checks out. And then I'm going to run metal between, nope, not poly, because that's going to tie everything together. And let's see if I get an error. No. So why did I choose to use metal over polysilicon there?
So you could run the other ones under it.
Well, but that gate connection down at the bottom transistor on transistors M1 and M2 aren't going to go under it, although that would be a good reason to do it. I'm doing it purely because it's way less resistive than the polysilicon, right? Even the doped polysilicon has a resistance of something around 100 ohms per square, whereas the metal has something around less than 1 ohm per square. And so if I want to make sure that these gates are at the same potential, I need to make sure that the resistance, there's not going to be an appreciable voltage drop over that. There shouldn't be any gate current flowing or anything like that to cause a drop, but I'm just trying to play it safe here. Okay, so let's review just to make sure I haven't made any wild errors here. So the drain of transistor M1 is tied to the source of transistor M3. That's supposed to happen. That is also tied by this piece of metal to the gate of transistor M1, which looks correct. And the gate of transistor M1 should be tied to transistor M2. That's correct. We have our source here. So we'd still need to do our body connection, right? So I might revisit this piece of metal in just a second because of our body connection. But let's go ahead and put down some P-well contact. And so what I'm going to do, let's see.
Dr. Hartman, how
Yes.
are you going to get a source of 1 and 2 to ground?
So that's what I'm about to figure out. I might need to make that run that metal run that connects the gate of M3 to M4. I might need to move it up a metal layer.
Okay.
So that's what I'm trying to figure out right now. But let's see, let's make this 50. Is that too wide? Not quite wide enough, actually. Let's make it 60. So there's a body connection there. I'm going to be doing something slightly different here. Let's make this 20. So what I'm doing, or at least what I'm attempting to do, is to make a grounding ring around this whole thing, because we have all of these NMOS transistors and we want the body of all of them to be at ground. I'm effectively just making a ring around the whole thing. I'm going to tie it all together. No, I want the active. All right, so I'm going to try something different here. Why can I never? Get the green to connect to the green when I want it to. All right. Well, we'll just do it like that then. This is not giving me any errors. Let's make this guy taller, maybe 40. There's 40. Yeah, that'll be okay. And let's press F5. All right. So what that ring is going to do is it's effectively going to force that whole P-well region around all of those transistors to be at ground. So I've got a solid body connection for all those guys. Now I need to tie that source to that the source of 1 and 2 to that grounding ring. And then as I think it was Grant asking, if I put that metal layer between here and here, the issue is that even though it's not showing a dot that they are connected, they exist on the same metal layer, which means they touch each other, right? So that would be grounding out the gate of transistors M3 and M4, which is entirely not what I want to do. So to get around this, we're going to put in another contact, right? So this metal polysilicon 1 contact, not what we're looking for. We're going to look for metal 1 to metal 2, which is this guy right here. I'm going to drop this fella over, wire it up, drop another one over here, wire it up, and then I'm going to slide these metal 1 to metal 2 contacts over because I am allowed to stack my contacts like that. And now if I click here to here, it's still doing metal 1. So let's select metal 2. And there we go. And so now I have my gates of transistor M3 tied together to the transistor M4, and I'm not going to effectively short out those two transistors. I have accidentally formed a small metal 1 to metal 2 capacitor, but we're talking about, let's see, so the size of these runs is, let's see what the width is here, 4. So 4 lambda would be 1.2 micron by 1.2 micron capacitor. So that parasitic capacitance should be very, very small there. Okay, so that's the bottom portion of our transistor or our current mirror. Or actually, no, it's not, because I forgot to put the drain contact. So let's scooch this guy over. I'm missing this, the drain of transistor M4. That'll work for me. Let's make sure it passes 4 errors. So it's yelling at me that effectively, I think it's yelling that these aren't stacked. Now it's 5 because I think they're too close together, yeah. All right, let's pull this guy out here. Let's delete that metal. Delete that metal. This guy 65. Those guys are too close because they're not touching. Before we do that, let's make this guy 65. I have 7, goodness gracious. So it's trying to tell me that that width there is 2.5, and it can't be. Three errors. I'm getting better. Spacing less than. Four errors. All right. Okay, let's see. Ground ring, attempt number 2. Let's move this guy away and this guy away for a moment. Check. 6 errors. What are the errors now? So those guys are still too close. So move this guy down 1. That metal layer that's connecting them is, select the metal. All right, try it from this. No errors. Still no errors. No errors. No errors. Great. All right, we got our correctly. It's not too close to anything. Everything seems hunky-dory here. So now let's tie that. Still no errors. All right, now we're cooking with gas. So the last thing that we need to do then is to connect our PMOS transistor. And we haven't really discussed the size of this particular one because this guy isn't being used as a resistor. We're simply using it as a current source. So we have a situation here where effectively our electron mobility in our NMOS transistors is 3 times as large as our hole mobility in our PMOS transistors. It's actually closer to 2.5, but we'll just call it 3 for now because that's what the book uses. So we're going to size this PMOS transistor. Instead of being 10 by 2, it'll be 30 by 2. And it's purely due to the 3-to-1 ratio of mobilities. So let's get a PMOS. Let's see, we need a 30 by 2, which it might be smarter. We'll do it 30 by 2 like this right now. We had all the other ones oriented up. Okay, to rotate it like so. Put it up here. Let's see. One error. I bet it's just telling me, yeah. There's an overlap of N well and P well. They no longer overlap. We're going to need to do a body connection for that guy. So what I'm considering here, right now this is a 30 by 2, but what I'm considering doing is 3 10 by 2s in parallel so that it'll more closely match the physical dimensions of our 4 transistors here on the bottom. Where, just to be clear, I never did this guy. The drain. So I have that guy. My other option, to be clear here, satisfies. PMOS. All right. Let's do another PMOS over here. That spice. Active. Another P active over here. All right, so I have these 3 transistors, and for them to be in parallel, that means my sources need to be connected to my sources, my drains need to be connected to my drains, and then all my gates need to be tied together. So let's look at how we can do that. So this is tying source to source. This is tying drain to drain. I'm trying to think. If I should have another PMOS transistor here, right? Because when we tie all these gates together, it's obvious that the length will just be 2, but for my width, I have, so let's call this guy over here source. So that's 10 width plus 20 width, or plus another 10 gives us 20. So I believe I should have another transistor. Let me check real quick. Yep, that's only giving me 20. So I need to throw another couple of PMOS transistors in here at least. There's no simulation, set spice model. Rotation. So this metal was too close, which means this metal is also too close. All right, no errors. So now we need another P active region over here. Five. No errors. All right, so one important thing here is that we all need to agree that this is a 30 by 2 transistor. And I know I don't have the gates tied together. I'll do that momentarily. So the reason why I'm calling it a 30 by 2, even though it is 4 transistors, is again because we have this width region from here to here is 10 plus another 10 plus another 10, all in parallel makes 30. So we should be good to go there. For our polysilicon, I don't want contact. Let me delete this guy real quick and this guy real quick. I want to see if it will let me.
Dr. Hartman, why does the third transistor not make 10?
So when we had, let's see, can you see my mouse here? So when,
Yes, sir.
all right, let me get these guys. So first, let's see if this works. It does, okay. So what I'm saying is that when we only had up to the third transistor, so if this guy over here weren't connected, this distance from here to here is 10. And then we have another distance from here to here, making 20 for our source or drain. If we don't have this other transistor also to give us the extra 10, it's not a 30 by 2. It's only a 20 by 2 when we have the 3 connected, because our total width would be 10 on the source plus another 10 is 20, and then 10 plus another 10 is 20. Adding this other transistor gives us a width of 30. At least on one side, and we probably need to add so that it's not, hold on, let me. All right, so those are all tied together. What we'll do in a minute is we'll simulate it and see. And so what I'm thinking is we may need to add an extra resistor, because right now, if this guy on the top here is our source, it has a length of 30 or width of 30, but our drain doesn't. It only has a width of 20. So if we add another PMOS, let's call this 10 by 2, rotation 90 degrees, apply. Set our spice model. No. PMOS 5, 90. So that gets tied to there. Tied to there. All right. So my argument, and we'll find out whether or not I'm right momentarily, is that this guy on the right-hand side is the same as this guy.
Do you need to tie the source of the third transistor to the point, but I can't. Like third over.
So, oh yeah, okay. Yeah, this guy top here. Yes, so we need a metal connection. Let's control Z. Let's get this guy.
Dr. Hartman, there's something going on with your mic. I'm not sure if you have like an external that came unplugged or something, but yeah, we can't really tell what you're saying. Oh, well, never mind. It appears it's fixed itself.
Oh, that's too close. All right. 2 errors. Let's see what these are. Overlaps. So that likely means, yeah, it didn't get connected. Errors. Okay, so I got all my gates and sources tied up how they're supposed to be. So just for the sake of argument here, let's say I'm going to tie this guy to VDD. Tie this side to ground, GND. And this will be my voltage G. Let's call it VGG, just for the sake of argument. And I'm going to throw on some P active on this guy real quick. We're going to run a simulation and see if our weird kind of folded looking 30 by 2 transistor behaves similarly to our simple 30 by 2. What did I just do? See, I'm worried right now if I actually, let me call this one. No. I have two exports with the same name. My best guess is it's going to freak out. So I've got the voltages tied together. Now I need to tie grounds together. Just for, no, I don't know what that just did. All right. So now I need to write some spice code. All right, so let's see. It's going to be multi-line text. So I'm going to set VDD as a 5 volt DC. Yeah. I'm going to set VGG1 as a, let's say 4 volt, because our threshold voltage for our PMOS is, I think, around 0.9. So it needs to be 0.9 lower than VDD to turn on. So that seems reasonable. I need to do, let's see, the transient analysis for 1 second and include C:/electric/C models.txt. Here's, I believe, properly set up spice code where I'm just applying DC voltages to all the pins, where ground is ground, so I don't need to specify what that one is. So I'm applying 4 volts to the gate of both of the transistors, 5 volts as my positive power supply voltage that I'm applying to the sources, because this is a PMOS, but in the grand scheme of things, it won't particularly matter. And I'm grounding the other one so that I can just measure current. So let's simulate and look at the currents flowing in. Can't find definition of model. Okay. So it gave me an error, LT Spice gave me an error because I never set the spice model for this big transistor. So I need to do that real quick. All right, no errors this time. So let's see what's what. So we'll add a trace for so many things because let's see. ID for MPMOS 0, which should be the current flowing through that big leftmost transistor. And it's looking hinky like it might not be turned on, but we'll look at that in a second. Might be because I didn't load it with anything, so it's got a really big and ID for that very last one. Not looking like they're the same. Let me try something else real quick. So all I'm going to do is I'm going to load these transistors with a resistor. That's ground. Let's make them both for the sake of argument. 65K seems reasonable to me. All right, so I've got all that kind of stuff still tied together. So not giving me any errors. You guys are still seeing electric. DMP MOS. So on my big one, I'm getting approximately 11 microamps, and on my other one, I'm getting 2. When they should be behaving practically identically. So I don't know. Let me, well, we're running at it. Well, we're out of time because it's 9:50. I'll have to think about this. But what you guys could do in the interim, and I know you've got your test to finish up, but you could simply just wire up this big 30x2 guy and connect it where it needs to connect to the 2 cascoded NMOS, or the cascoded NMOS bit at the bottom. And then we'll play around with some stuff on electric and get cracking on either our biasing circuitry or our differential amplifier stage on Thursday, whichever one I decide to do. So I'll talk to you guys on Thursday. Have a good rest of your day.
Dr. Hartman,
Yes.
I don't know if you had that video from last Thursday, but if you do, is there any way that you could post it?
It is on YouTube right now. I just need to put the link on Moodle. But if you go to any of the other videos to have access to my YouTube channel, it's been up since yesterday.
Gotcha. Okay, I'll go take a look. I shouldn't see it on Moodle, so I'll go take a look though. Thanks.
Okay, no problem.